Hey, it's True again with another development guide from phyTech. Today we're working on LVGL graphics stack on the phyCORE-i.MX 8M Plus. Let's get right into it. So, we're going to open up our terminal here in Ubuntu 20.04 and we're going to navigate back to our BSP that we set up in a previous video. We're going to source that development environment. And now here in the build directory, all we have to do to add LVGL support to our PD24.1.0 BSP is to grab one of these modular meta layers. We have one prepared for you, specifically for Meta LVGL, or for LVGL, and it's called Meta LVGL Demo. I have that here on my GitHub right now, and it's public. And we want to make sure that we grab that ScarthGap version, so that'll be in line with the Yocto version used in PD24.1.0. Go ahead and run that command. We navigate back to the build directory, and we can enable that meta layer with this bitbake layers add layer command. Let's give the path to the meta layer we want to enable. And when we've done that, we can double check our bblayers.conf and just double check that Meta LVGL demo is enabled along with all the other meta layers that are provided and enabled by default in this BSP release. Now, let's navigate back to that real quick. Just take a quick look around. So here we're going to have some recipes for graphics, recipes for images. If we go into the images, looks like we have a new LVGL demo image prepared. So rather than building phyTech headless image, which is no graphics, or the Qt6 demo image, which is Qt6 specific, now we have a new image called phyTech LVGL demo/image. Alongside that, we have recipes graphics. So it looks like this recipe is going to provide us the demo itself. Looks like there's some associated files here. And so looks like this meta layer is also going to set up a systemd service that will start that application on automatically on boot. And then there's another in recipe graphics. We got Wayland. Oops. In this file, Weston init bb append, this is appending to the existing Weston init recipe, and it looks like we're providing this weston.ini file. So what is that? That is going to be in this Weston init path here. Weston ini, here it is. And so this is actually it's applying the Weston compositor change that we did in the previous Qt6 demo image video, where we switched the default display from the HDMI port to the LVDS. Well, this file is going to introduce this change so that it happens at build time. We don't have to do it at runtime anymore. And this is a good reference for accomplishing that. Before we go ahead and kick off that build, there's one important step that I missed. We'll have to open up our conf/localconf, navigate down here to the end of the file, and we're going to have to add this line. Now, what does that do? This line here is going to change the preferred version for Weston, provided by this i.MX NXP BSP recipe, I believe. We're going to drop the version down from version 12, which is the latest Weston provided in, well, it's not the latest Weston. I think it's the Weston version provided in the latest phyTech BSP. And we have to drop that down to version 10. And that's because LVGL has a specific requirement for what is it called? WL shell extension, which is provided for in Weston. This was deprecated back here in version 10, but it has that support. Version 12 officially dropped it, and so we're going to have to, for now, drop the version of Weston down to version 10 to enable the LVGL demo to run. And in the future, phyTech may or may not upgrade that LVGL demo to support the latest version of Weston as a reference for everybody. But for now, we're going to downgrade the Weston version and allow everything to build. And so now we can go ahead and go kick off our build with this command again. All right, and now once our build completes, we can navigate into deploy, amplify, and then it appends the distro version there to images, and then Fiboard, the machine that we're building. And here we can see our LVGL demo image Specifically, the wic.xz is the one we want to flash. Now, we can go ahead and flash that to an SD card. All right, and now that's completed. Let's go ahead and boot it on our hardware. So take that LVGL demo image SD card, boot up our phyCORE-i.MX 8M Plus development kit using that card, and recall that our meta layer, the meta LVGL demo layer, automatically configured the Weston compositor to use the LVDS display. So we should see everything come up here by default, and there it is. This is our LVGL demo. This is actually, I believe, provided from the LVGL project itself, and we've adapted in this meta layer to work on our phyCORE-i.MX 8M Plus. And so, yeah, that's the out-of-the-box demo. Let's go ahead and work on building our own demo now. To make that demo, we're going to have to first navigate back out of, actually, key here. We don't want to overlap build environments. So recall that this is our terminal session here that we use to build the BSP in the image that we just produced. We're going to want a new terminal session, navigate out of there, and we're going to want to source our SDK environment. So the SDK environment should be separate from the BSP environment. So new terminal, we'll source that again. If you recall, we installed this in a previous video, like so. And then we're going to have to get the LVGL project. So let's quickly make a directory for that and navigate into it. And then we'll clone the demo LVGL Git repository. Navigate into there, and then we'll have to recursively pull these other repositories here they're like child repos. Alrighty, so now we have our LVGL set up here. The demo itself is really realized with this main.c file, and then LVGL backend support is going to be provided by the LVGL repo here, and then the driver support is provided here in the separate repo. In order to go ahead and build the default that we have here, and this is going to sort of reproduce what we showed on the development kit, we're going to create a build directory. Now, this is a CMake project, as you can see by the CMake list.txt. So we'll have to create a build directory, navigate into it, run CMake, and then we can go ahead and run make. Now, be sure that we have our environment sourced for the Yocto SDK, and I always like to use the CC variable to double check if that environment is sourced or not. Now we can just run make. Perfect. Now that that's done, we can take a look in our build directory and see the LVGL demo-WL executable binary here. That is our demo. We need to transfer that over to our hardware and run it. And a very convenient way to do that is to just go ahead and grab the IP address of our development kit, hop back over, and we can CP this file to root at that IP address. Oops. We'll send that to the home directory, and we'll run an SSH command here. This is going to create an SSH tunnel where we can access a console on, or the shell on the hardware. We're going to run this -t option. I believe this allows us to start and end processes just right here on the command line. We're going to do that here with that target device at that IP address. And what we're going to run is this command. It's going to be, we're going to basically run the executable itself, but we're also at the same time going to declare this environment variable xdg runtime dir to run user 1000. This is going to give the executable, the LVGL demo, the context it needs to run the application and draw the graphics on our Weston display. So if I go ahead and hit that button, I'll hit enter here, switch over, file will be transferred over, and it should start. Now, a key thing here is because this is the same application, it's not super clear what's happening. So let's go ahead and stop the LVGL demo. I can't remember the name of it. Just do a quick grep for it. That's the name. So system control, we're going to go ahead and stop that service. We should see, yep, the demo went away. And now if I hop back over to my terminal here, I can start it from the host. We'll just run this again, switch, and there. Missed the transition, but I'll kill it and start it from the host again without touching the target console. So perfect. Now we've recreated our LVGL demo. Let's go ahead and get into a custom GUI. All right, and so we can go into our existing project and modify that main.c. This is the default demo that we just showcased here on the hardware, and we can really see too the demo itself is really just called with this demo widgets function here. We're going to get rid of all this code, and we're going to go ahead and populate this code I have written off screen. What do we do here? We have included a number of things, but the big key one is this GPIO-D library that we've included. That's going to give us the ability to toggle our GPIO with our button presses. And then I've declared which GPIO that's going to be. And then a helper function, this is going to request our GPIOs if they're available. And we have a toggle LED function and a button event callback. This is going to tie the button that we create in the GUI to the toggle LED function itself. And then down here in the main function, we've this is all the default stuff. We've added the button itself. We've created a label on that button, and then we tied that button to the callback, which calls the toggle LED function. Go ahead and write that. Now, note that we added the GPIO-D library to this project. Now we're also going to have to modify the CMake lists file, and this is going to allow make to find our library. We just add that GPIO-D to this target link libraries function in CMake, run CMake again, and then we can just run make. Here I'm going to run make with this. That's actually a typo. I'll just type it out. This is going to allow us to leverage parallelization using the number of CPUs our host machine has. We'll be able to kick off that many parallel tasks, and so make will build a lot quicker this time. And then we can go ahead and SCP our demo again. Hit enter. Switch over, and now we can see the updated GUI with a button. And as expected, it should toggle LED. Basic hardware control with an LVGL GUI.